Okay, so time to get started. It's hard for me to believe today's the last day of classes. Feels like we just got started this semester, but anyway, here we are. So we have about a section and a half left to cover, and the section, so section 6.5 that we haven't started yet, is a really quick one. So that's good news, right? So this is actually going to work out just fine. So one other comment I wanted to make is that on the final exam, our last remaining exam, final exam, note that most of the material for the course has already been represented on a midterm exam. Some of the material has not been represented on a midterm exam for specifically section 6.4 and 6.5. Right? So with that in mind, so just, keep in mind my goal is to have, broad stroke, roughly speaking, kind of uniform representation of all of the content of the course in total over all of the exams. And so for your consideration, the stuff in 6.4 and 6.5, it hasn't been on a midterm yet, so it'll probably be weighted a little bit heavier on the final than perhaps it otherwise would have. So anyway, for your consideration. Okay, so let's finish up with 6.4 then. Let me remind you what we did with 6.4 last time. We had this formula that I did not prove. No problem. This formula, though, for how to find a particular solution to a non-homogeneous system. Right, and so this example here we did last time, pretty quickly, but it was just it's just an immediate application of that formula. So there you go. You identify the homogeneous portion. You find the fundamental solution matrix. Now, of course, we spent a bunch of time talking about how to do that. This one is diagonalizable, and so you use the methods from 6.2 to write down the solutions and therefore the fundamental matrix. You got to invert that matrix, right? And then et cetera, et cetera. So specifically, notice that after you've inverted it, the next thing you've got to do is you've got to multiply by the g vector, and then you've got to take an antiderivative of that vector. And then having done that, you've got to multiply back by the M matrix. So there's a lot of steps involved. The annoying one, you might say, is notice here, this M inverse G, that you have to take an antiderivative of. Well, gosh, we're taking an antiderivative of a product of an exponential and a factor of x. In fact, we're doing it twice, right? So it's a little annoying. You have to make sure you can, among other things, you have to make sure you remember how to do all that single variable anti-differentiation, right? And you got to make sure that you can do it without making errors, easy errors to make. Okay, so there's a bunch then of algebra that I kind of glossed over right there. So make sure that you can do all that. Okay. Last step, again, multiplying back by that M matrix. Keep in mind the result of this antiderivative is a vector, and that vector antiderivative is multiplied by M to get our particular solution, which after some simplifying ends up being this. Okay. All right. So going on from there, I want to just show you another example. This is a second example. It's also kind of an example of a different idea. Y'all will probably remember that we saw some examples back in chapter 4 where the right-hand side, what I loosely call the right-hand side, had trig in it. And the slick move, was to say, well, you know what, let's forget about that equation. Let's look at the associated complex equation. Let's solve this. By the way, why are we solving this, the green instead of the yellow? Because this is easier, ultimately, right? In a lot of ways of algebra and calculus, exponentials are easier functions than trig functions. Right? So it's one of these sort of contradictions. I mean, look at the name as complex. That seems to make it sound like it's going to be complicated, right? But it's actually algebraically less complicated. It's easier to do. And so we're going to find the same thing will happen here. We're going to abandon the real initial equation that we were asked. We're going to look instead at the complex version of it. We will solve the complex version, and having done so, then, well, we'll just look at the real part, just like we did in Chapter 4. Okay, so how do we deal with this? Well, it's the same process as in the past, the last example. So notice the homogeneous part. Yeah, we've got a different G, right? But the homogeneous part by itself is the exact same as the previous example. So we get the same M inverse, therefore, right? So a certain amount of the algebra is kind of already there for us. Okay, next we've got to multiply M inverse, which is listed on the previous page. We've got to multiply that by our G. Multiply that out and you get this. All right, notice it's all exponentials. Very nice. Okay. What do we do to M inverse G? Well, back to the equation. M inverse G, you take an antiderivative of it. And here's where you're going to see the benefits of passing to the complex equation. And that is taking the antiderivative of M inverse G. The antiderivative of that, again, look at what we've got inside of our integral. What we're taking the antiderivative of? Pure exponential. Among the easiest antiderivatives in the world to compute. Super easy. Now, we're not done yet. There's some cleaning up that we have to do. One more step of algebra and a little bit of cleaning up. But that's relatively easy calculus. Yeah, I saw a hand somewhere. Yeah. Yeah, that's the rule for taking an antiderivative of e to the ax. It's 1 over a e to the ax. It's a substitution. If you just kind of write down u equals ax and go through that whole game, 1 over a ends up being part of the answer. Yeah. Anybody else? Everybody good? Now, before I go on, let me, I want to, again, brag on this, the benefits of this idea of, again, we abandoned the real equation in favor instead of the complex. Well, what if we had not done that? What if we had said, all this complex stuff is annoying, I don't want to deal with any of that. I want instead to just deal directly with that. Then that is what we would multiply by M inverse. These i's would go away, seemingly a win, right? But then notice these cosines would show up. Right? So this is what you'd be taking an antiderivative of. Right, and let's consider this prospect, taking an antiderivative of, two different components, again, right? But each one of these two different components is an exponential times a trig function, right? Now, do y'all remember, give me 2 seconds, do y'all remember how to do antiderivatives of exponentials times trig functions? This same question came up back in Chapter 4 when we were considering, a kind of an analogous scenario. And the punchline is exponential times trig. To do an antiderivative, you have to do an integration by parts followed by a second integration by parts, minus signs on your minus signs. It's very sort of precarious in terms of oopses. And after doing two integration by parts, you then have to, make the clever observation that the integral that you're interested in, you still haven't computed it, but it is equal to a bunch of other stuff plus itself, and then a multiple of itself, and you have to whip that over to the other side, and divide. It's a whole thing, right? These are hard integrals. It's the punchline, right? So that's why this is undesirable, right? The real version of the equation involves hard calculus, whereas the complex version of the equation involves easy calculus. Yes.
Do you have to take into account the sign aspect, the sign part of the e to the I?
We don't have to worry about it. So what we've got here you're quite right that in this equation here, there's really kind of two equations hidden inside of this, right? There's the real part and there's the imaginary part. And the real part is where the cosines are, and the imaginary part is where the sines are. The thing is, I'm not solving this one component at a time. I'm solving it sort of all at once with, complex algebra. And so I don't have to think about what's going on separately with real and imaginary. They just kind of automatically both get dealt with when I do this as a complex valued function. And then at the end, when I'm done, I just only care about the real part. So so basically I can just completely ignore the imaginary side. I mean, it's going to be there, but I can just kind of ignore it and end up not using it at all. Yeah. Anybody else? Okay, so I hope you're with me on the pros and cons here. I think there's a lot of advantages as you use the complex equivalent. Give yourself the benefit of easy antiderivatives. And then yes, there is a cost, a little bit of a cost, and that is you have to do a little bit of complex arithmetic to rewrite that. When you're done, and then there's going to be a little bit more complex arithmetic to come as well, but it's a relatively small price to pay. Okay, moving along. There's our antiderivative. Don't forget the antiderivative gets multiplied by the M matrix again, thus giving you altogether your particular solution. Again, some kind of inconvenient arithmetic a little bit, not a lot. It's not that bad. I have two complex fractions, different denominators. No big deal, right? So you got to simplify that, and then you have to then multiply out. You'll notice that we have complex number in rectangular form times complex function in polar form. To multiply those, you've got to turn your polar form into rectangular form. And then it's just a FOIL thing, right? Just multiplying real plus imaginary times real plus imaginary, and doing that and looking at the real portion. That's all you're actually interested in anyway. This is what your particular solution ends up being. So again, a little bit of complex arithmetic. It's not that bad. If you would like, just for comparison purposes, solve this problem directly like that. Ignore all the complex. Do that integration by parts twice in each of two different components. And again, there's going to be some details, right? And then see which one you like better. I think this is the better one. I think using the complex move is the better move. Okay. Any questions? Everybody on board? Okay. So let's go back to our first example. Here it was. Here was the initial question. We went through this whole process. And let's see here. Let me try to get this all on the same page. Went through this whole process, and here was the answer. And there's something unsatisfying about this whole story. We started off with a question that didn't have any exponentials in it. We ended up with an answer that doesn't have any exponentials in it. And yet the process of getting there involved dealing with a lot of exponentials. Right? And it just kind of makes you feel like that. I mean, it was a relatively simple looking question with a relatively simple answer. Don't you feel like there should have been a simple process? Right? Other than this, magic box, you put the ingredients in and turn the crank, and then out comes the answer, but however inconvenient. The answer is that, there's a arguably easier way to solve this problem. Let me show you how this works. It is, roughly speaking, to do a rip-off of section 4.3. Remember in section 4.3, we look at a non-homogeneous equation, we look at the right-hand side, we speculate about, given that this right-hand side takes a certain form, it seems like the solution is going to have certain kinds of terms in it. I mean, the thing that's going to cancel or balance with this has got to come from somewhere, right? And so speculate about what kinds of terms ought to exist in your y. Call that your guess and leave yourself some fudge factors and see if you can make it all fit. Right? That's roughly what we do in 4.3. So same thing you can do here. So looking at that right-hand side, you see we have a constant vector times x. Seems plausible that a constant vector times x ought to be part of the solution. Oh, but wait a second. If I have a constant times x as part of the solution, I'll be taking a derivative of that. That's going to make constant vectors show up. Well, there's no constant vector on the right-hand side. There's no constant vector in the current guess. Where would that constant vector get balanced? Right? So you speculate maybe there would be a constant vector in the solution as well. It's the same rationale that we used back in 4.3. So that together suggests that maybe this is a solution. Something of this form. Note the fudge factors. I'm not saying I know what this A vector is. I don't know. Let's just call it A for the moment. We'll figure it out later. I don't know what this B is going to be. But I feel like something like this kind of ought to work. So, just like we did in 4.3, take that, plug it in, see what the equation becomes. The derivative of that guess is the B vector. Right? We've got this this matrix that I'm rewriting as just A times our guess plus our G. Right? So the equation becomes this, and now I can just focus my attention on this. Can I solve that equation? And keep in mind, I want to solve this equation for all values of x. That means this equation has to hold for all values of x. That means that the x terms have to all sort of balance, as it were, right? And all the constant terms have to balance. So that one equation gives me these two equations. Here. That and this. So here, let me color code better than that. Here's your x terms. Those are the coefficients of the x terms. And then here are your non-x terms. Everybody see what happened there? Grouping the x terms together, grouping the non-x terms together. Now I have, instead of one big equation, now I have two separate equations. And so what it all comes down to is, can I find A and B that satisfy this pair of equations? And it just becomes a little bit of algebra. Now, consider your algebra strategically. There are lots and lots and lots and lots of solutions to this equation on the right. Right? Take any A vector, multiply by the A matrix. There's a B vector. That would satisfy this equation. That's too easy. That's not what we're looking to do. Right? Notice that it's going to be harder to satisfy this equation. So work on this one first. Start with the yellow equation. Find that B vector. There might only be one solution to this B vector. Once you know that B vector, then solve the blue equation for the A vector. And so you'll notice that's what we do here. That matrix is invertible. So this yellow equation tells us B. Once I know B, the blue equation tells us A. And plugging back in at the very beginning, let's see, I guess I can't fit that in there. But this gives you then that particular solution. How are we doing? Is everybody happy with that? Any questions? Now, this is a lot easier than the thing we did several pages back. Integration by parts, dealing with exponentials. That was clearly more work. This is guess and check. No exponentials anywhere. This is all easy algebra. That's really nice. So, question, why would you ever do anything other than this? And here's the bad news. This guess and check method here in section 6.4, I'm not going to be able to give you this super powerful theorem like we had in section 4.3. In 4.3, we enumerated a very broad category of possible right-hand sides. very broad. Monomial factors, exponential factors, sine and cosine factors, anything of this very broad form. Here's the guess that will work. That was really, really luxurious, right? We aren't going to have such a thing here. There's too many different cases. There's too many different, well, what if this? What if that? So there is going to be a component of kind of guessing. Keep your fingers crossed. Face the possibility that your guess that you thought was going to work might not work. So there's a component of risk in doing it this way. Nevertheless, I think that's the move. I encourage you to do it this way, right? Take a guess. It's probably going to work out. Yes.
So by saying we guess might not work.
Yeah, I've got some. I'm going to show you some examples of where it might not work. Go ahead.
I was just going to say, is that not? Would you try a guess of a different form? Like,
yeah, that's right. That's right. If your guess doesn't work, would you try a different guess that you have to again strategize what different guess might help me resolve my problem? But yeah, a different form then would be your next thing to try. Yep. Okay, so let me show you a couple more examples.
Okay. Alrighty. So here we go. Notice that our right-hand side is a constant vector times an exponential. Now this is a different form from the previous example. So we correspondingly make a different guess. And how about constant vector times an exponential, right? I mean, if you take constant times an exponential, multiply it by a matrix, you're going to get a constant times an exponential. When you take a derivative, you're going to get a constant times exponential. You're going to have constants times exponentials all over the place, and the hope is that you can make that balance out just right. So take this as your guess, plug it in, the equation becomes that. Notice you can cancel your common factor of the exponential in all of these terms. Now I just glossed over, of course, all the algebra. Right? So think in terms of how that guess plugs into the equation. Make sure that you can get down to this. And it all comes down to this equation. So whatever your right-hand side, whatever that constant vector is, that's going to tell you your right-hand side in an equation in which you hope to be able to solve for A. Yeah. And usually this works. Most of the time this works. Sadly, this doesn't always work, right? Here's a case where this wouldn't work. What if A minus Ri is not invertible? Right? What if this matrix is singular? Said differently, what if R is an eigenvalue of the A matrix? Well, then you have strong potential that there won't be any solution to this. And so this is, somebody was asking earlier, what can go wrong? And this is an example of kind of thing that can go wrong. We guessed wrong. Right? So this form doesn't work. So how do we fix it? Per the speculation from the crowd, change your guess. Now here's that same form of a right-hand side. Constant vector times an exponential. Previously, we guessed constant vector times an exponential. Optimistically, we had reason to believe, that seemed very plausible that this would work out, and it didn't, right? So what do? We add an extra term. Now, why am I going to add that as an extra term? This is wishful thinking, right? This is not, I can't derive and tell you, where exactly this comes from, but my speculation goes like this. If I take this green term here and add it into my guess, notice that when I take a derivative, think about what happens when you take the derivative of this green term, on the left-hand side over here. The derivative, we've got an exponential times x. There's going to be a product rule. Somewhere along the line, I'll be taking the derivative of that x, and I will get another term that is a constant times the exponential. Right, so this is a way of sort of sneak adding an extra player into the mix, and hopefully that extra player will allow it to work out. And roughly speaking, that's what's about to happen. Does everybody see the motivation here? Seems like a reasonable thing to try. Okay. So here we go. Plug that into the equation. The equation turns into this. That's algebra. Again, glossing. Right? Make sure you can do that on your own. Common factor of the exponential in all of the terms cancels. Now there's a bunch of terms in here, and you've got to group together the like powers of x. Here is a term that has an x in it. Let's see here. Here is a term that has an x in it. Those give you these. And then there's a term with no x's. 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 That gives you this. Okay, so all of that business above simplifies like that, and thus gives me two equations to solve. And now again, it's just algebra. Now there's some twists in this algebra, but we've got it down to, can we find vectors A and B that make these equations work? Does everybody follow me so far? Does anybody have any questions so far? Okay. Yeah.
What's V? What's that V vector?
I just got tired of writing 1, 3 or 1, 2, I guess it was. So this
Is that an eigenvector?
that's V. It's just the vector that was given as the right hand side.
Okay.
Yep. No assumption about it being an eigenvector. That's right. Okay, so now keep in mind we have this issue of, is this matrix invertible? If the matrix is invertible, well, everything falls into place, no problem. But this matrix is not invertible. 4 is an eigenvalue of the given matrix. A minus 4i is singular. So we've got singular. We have two singular equations. Now, in this scenario, this is a good news, bad news situation. It's a good news here that 4 is an eigenvalue. What that means is that there isn't just one solution B, right? There's free variables in this equation, right? This is a singular matrix. There's no existence problem. The right-hand side's 0. We know a solution exists, right? So, good news. We have a free variable. There's infinitely many solutions, and this B can be anything. Can be anything times that eigenvector -1, 1. Okay, so that's the good news side of this story. The bad news side of this story is, you look at this equation, this is not a homogeneous equation. Here I do have an existence problem. There may be no solution at all on the right, so we've got an issue. So what we need to do is figure out how to sort of, balance this off. How do I find, is there a K? Is there, of these infinitely many solutions I have to choose from, free for nothing in the B vector? Might it be that one of them is exactly what I need to make the purple equation work? And it turns out that's what happens. So this is just kind of details, but here we go. Taking this from the left equation, plugging it in on the right, the equation becomes this, which I rewrite like this. A minus 4i is that matrix. Don't forget what V was. V was 1, 2. Right? And so I'm down to now this matrix equation. And can I solve for A? Okay, so here's where you see the problem. Can I solve for A? We have a singular coefficient matrix on the left. It's not 0 on the right. There's a possible existence problem. Right? So this is in fact exactly a chapter 1 question. Y'all may recall long ago in chapter 1, system of equations, variables on the right-hand side, and how do you decide when, for what values of K will a solution exist? You take the equation, you row reduce. You just go through and row reduce this, and you will have a row of zeros on the left. You will have some expression
in the corresponding spot on the right, just pick the value of k that makes there be no contradiction. Right? So you can totally do that. Now I'll show you a different sort of smart alecky way around this instead. Notice that you can rewrite this as 3 times negative a1 minus a2 and 2 times negative a1 minus a2. So what you've really got then is this thing is a vector whose coordinates are clearly in a proportion of 3 to 2. Right? I mean, just look at the way this multiplies out. This multiplies out like that. That means that the first and second coordinates of this left-hand side vector are in a 3 to 2 proportion. If there's going to exist a solution, that means that these things have to be in a 3 to 2 proportion as well. That tells me this. This is a clever move. You don't have to do it like this if you don't want to. If you just want a chapter 1 row reduce, solve for k, just like in section 1.1, totally fine, no problem. But this bypasses a little bit of row reduction. So anyway, so solve for k, and k ends up being 4/5. Still not done. Right now we know k. That means that we know b. Once we know b, now we know the right-hand side over there, and then we can solve for a. I'm skipping the details are just arithmetic. So here's your equation for a, and again, this is an easy row reduction, and here's a solution. There's actually, of course, lots of solutions, but this is a perfectly good solution, and all we need is one. And thus, our particular solution. So anyway, guess and check. If your sort of naive guess didn't work, then throw in some extra stuff, some extra terms that have the plausible possibility of helping. Work out your coefficients again. And altogether, I think this is usually a better bet, less effort, more. Let's see here, less inadvertent oops prone than the plug and chug method that we started with. Questions? Everybody happy? Okay. All right. Okay, last section, 6.5. Oh, by the way, you'll notice in the notes here, there's also I have some stuff here for section 6.6. This is not part of the syllabus. I have it in here just because it's a nice example of the ideas that we're about to learn about in 6.5. So this is just totally supplemental, not at all necessary. I don't think we're going to get to this today. If you're curious, it is kind of neat that we're about to learn some math that will help solve this problem. The problem being that instead of a mass on a spring, so suppose you have a mass on a spring hanging off of a mass, which is hanging off a spring. Right? And that seems, how could you possibly predict that behavior? It just seems completely chaotic. And it turns out it's not. It turns out that the way you answer this question is you just write down all the forces and you end up with a type of a differential equation that I'm about to show you how to solve. So anyway, kind of neato, but you can look at this on your own. Let's first talk about how to solve certain kinds of differential equations. I'm going to segue into this in what I think is the easiest sort of combination of motivations. I want to start off by going all the way back to chapter 4. Y'all remember these equations from chapter 4? All right, the constant coefficient case, by the way. And I'm going to make a kind of a smart alecky comment, and that is that all of these derivatives here are first derivatives. At which point you complain and say, no it's not, that one's clearly a third derivative. At which point my smart alecky comeback is, yeah, it is but it's a first derivative of y double prime.
Right? So, smart alecky observation. Believe it or not, that is the brilliant insight that makes this this process work. It is a first derivative. You gotta grant me. I mean, here we go. Let me just write this down. If I define these things here, y prime, and y double prime, to be new functions that I'm going to call u0, u1, and u2. Well, then this third derivative up here is the first derivative of u2. Yeah? Okay. All right. Okay, so in fact, I can, here, I guess I have to zoom out one notch here. I can solve for y triple prime there. Here it is. Whoops, let me not get ahead of myself. There's y triple prime. Notice that when y shows up in the equation, I'm replacing y with u0. I'm replacing y prime with u1. Right? Y double prime with u2, etc. Okay. All right. That is y triple prime. And then making the observation that y triple prime is u2 prime. Notice now what I have here in purple. I have a system, a first-order system of equations involving the variables u0, u1, and u2, right? And I can rewrite that system just like this. It's just a rewrite. The derivatives of u0, u1, and u2 given as functions of u0, u1, and u2. Right, so this little smart alecky move of replacing y and its derivatives with just new functions and observing what the connections are between the u variables and what the resulting initial equation says about the last derivative here, you get a brand new system of equations. So it's pretty neat how this has worked out. We started off with a chapter 4 style higher order differential equation, and we have ended up with a chapter 6 style first order system of equations, right? So there's been a sort of a trade-off. I mean, there is no such thing as something from nothing, right? So the profit, we got rid of all those high derivatives. The cost, now we've got a bunch of equations instead of just one. Everybody on board? Okay, so the big question that you're probably all asking, how does this help? Not clear. Right? Which would you rather do? Given the choice, if you had your choice between doing the red chapter 4 style equation or the purple chapter 6 style system, yeah, honestly, I think I'd just take the equation, the first equation. The characteristic polynomial, I'll just write it down. Right? We've got simple formulas. I don't have to worry about diagonalizable versus non-diagonalizable and all that jazz, right? It's just pretty much straightforward. And this is often straightforward. I mean, eigenvectors work out great and everything, but nevertheless, there's some potential hiccups here, and all else being equal, give me the initial. So this trick of being able to turn a chapter 4 problem into a chapter 6 problem is not clear how that really benefits us. Let's put a pin in that thought. It is going to turn out later to really be helpful, but for the moment, we just can't quite see it yet. Yes?
Why is the g in the equation negative for the y?
Let's see. Oh, did I? Oops. Let's see here. Yeah, I think you may have caught me there. I think you're right. I think this. So he asks about why is this a minus sign, and I think I was just being sloppy. Yeah, I think you're right. That's a plus. Good catch. Everybody see the fix there? Yep.
So if everything's a first order derivative of the one before it, does this still work if, like, you're missing the y double prime, like if A2 is 0?
Oh yeah, sure. It's just that there will be a function there will be a U1 that just doesn't happen to show up there, but it's fine. Yep, not a problem. Yeah. Okay, so now before we go on to why this helps us, I want to make some. Why did I just erase that? I need to keep that there. Before I go on to why this helps us, I want to make a shocking observation. This is really weird. I used to consider this to be really deep. I mean, when I first saw this, I thought this was a mysterious deep result. And that's this. Suppose you convert, as in the previous example, and remember the big idea here is that if you have a chapter 4 style nth order equation, then you go through that game on the previous page, clever observation, and notice that you then get a first order system. So suppose you do this. Suppose you turn an equation into a system. Keep in mind, in each of these cases, we have this idea of a characteristic polynomial. The characteristic polynomial there, think back to chapter 4. Our rules for making the characteristic polynomial for one of these nth order systems is you look at the coefficients and replace derivatives with powers of lambda, and there's your characteristic polynomial. On the other hand, in chapter 6, looking at that matrix, we have rules for how to find the characteristic polynomial that gives the eigenvalues and thus the eigenvectors and then ultimately the solutions, right? All that 6-2, 6-3 business. And it was a weird formula, but there was this formula for something called a characteristic polynomial. Now, at the time, I apologized for this term, characteristic polynomial. This is a totally different construction than the chapter 4 characteristic polynomial. Why would I use the same word to represent a totally different construction, working off of a totally different question than our previous, employment of that term, characteristic polynomial? Seemed super weird at the time, and here's why. These two characteristic polynomials will be equal. It's super weird, right? It's creepy even, right? That you go through this weird process of take your equation, do that song and dance on the previous page, find this system, take the coefficient matrix, subtract the lambdas on the diagonals, take the determinant, and then the resulting polynomial is exactly the same as the polynomial that you got over there. Isn't that amazing? I used to find this extremely counterintuitive. In fact, it's almost sort of not believable. Let me just show you that this actually works. I mean, there's a chapter 4 question. Here's the corresponding chapter 6 system. Here's how you would compute the characteristic polynomial. Multiply it all out, and you get that. It's exactly the same as that. Super weird. Almost enough to make you think there's something going on here, doesn't it? Yeah?
So if we're given the higher order differential equation, can we just get the characteristic polynomial from that and then...
Sure, yeah. In other words, if you want to say, starting with this, turn it into this system, but use that as your characteristic polynomial. Totally fine. Yep. Right. Okay, so not long after having seen this theorem for the first time, I was then given an explanation as to why this is actually not stunning, shocking. How could this possibly be true? This is extremely plausible. And I'm not going to prove the details here, but I just want to give you the plausibility argument. Why is it that, not why are these equal, but why should they be equal? That's what I want to talk about. And here's the idea. If I turn a chapter 4 equation into a chapter 6 system, well, the whole point to turning it into a new question is that their solutions are supposed to be the same. right? Go back to the first page here. The y is the u0, right? If you solve this system, the u0 is the y from that original equation. So said differently, they give you the same solutions. Okay. Well, wait a second. Where did the solutions come from? Think back to chapter 4. The solutions came from, by a certain construction, they came from the roots of the characteristic polynomial. In the chapter 6 system, where did it come from? Well, the solutions came from eigenvalues, which were roots of the characteristic polynomial. So if these two questions have the same solutions, which of course they do, well, then that means that these two polynomials ought to have the same roots. And if two polynomials have the same roots, that means they have the same factors, pretty much. We've got to worry about issues with multiplicities, but pretty much should have the same factors, and therefore it's not really at all surprising that they're the same polynomials. Does that seem kind of plausible? If they were different polynomials, they'd have different factors and different roots, and then you'd get different solutions, which we know can't happen. I think this is a weird little turnaround of intuitions that, it happens every so often, but it's always kind of wonderful, that something that seems almost implausible from the right point of view becomes extremely plausible. And again, there's not a proof. There's other details. What if there's multiplicities? What about these extra factors of x? And those are all details, but plausibility argument is this. Okay. All right. One last thing I want to show you before we go on. Let's go back to this question. I left this looming question of what's the point? How does this make my life easier? I just successfully turned a question into a harder question. Right? Why would you ever want to do that? Why would you want to turn a question that is susceptible to the relatively easy Chapter 4 methods into a harder question that requires the use of Chapter 6 methods? Here's the answer. It's really useful in a related question. Let's consider this mixture. Look at this question right here. This is a hard. We have not seen this before. Right here we have a system of equations. Yeah. Just like in chapter 6. Oh, wait a minute. This is second order. We never saw previous discussion. It was always first order in chapter 6. And then you think, oh, higher than first order. Chapter 4 is all about higher order equations. Oh, yeah, but not in a system. That was only one equation at a time. This is a kind of, combination of the worst of both worlds of chapters 4 and chapter 6. Right? That's a hard, we don't currently know how to do this. Right? But look what happens if we just apply the exact same smart alecky method from the couple of pages back. Same idea of, hey, check it out. Everything in here is a first derivative at most. Smart alecky observation. If you're allow me to, for example, talk about first derivatives of derivatives. Right? Because that's what the second derivatives are. Okay. So apply the same trick. Kind of rewrite everything. These two equations here, that equation turns into that, this equation turns into that. This relationship gives us that. This relationship missed. That relationship gives us that. And we again have successfully turned it into the analogous to the previous page. In this context, though, very important difference. This is not relatively easy problem turning into a relatively hard problem. Now, in this case, this is intractable problem I have no idea how to even get started on has turned into a, kind of annoying, but problem that I totally know how to do. Right? Nth order systems, we have no previous methods. A larger first order system,
totally doable. Okay, so let me show you how this applies to the this last example. Again, section 6.6, this business with mass on a spring on a mass on a spring. This problem, right? Our first intuition is that this is really, really, really hard to deal with. I'm going to have to gloss over the details because we are kind of technically out of time here. But if you just write down all the forces, this is just a little physics. Just write down all the forces. There's spring forces, there's friction forces, there's, whatever external forces may be acting. Write that all down and observe that you get a second order system of two equations, just like on the previous page, and therefore using this kind of a smart alecky substitution, we can turn that problem I don't know how to solve into a problem that is merely inconvenient, but that I do know how to solve, and you can crank out those details. Okay, all right, we're done with Math 216. I enjoyed having you all in the class. See you on Friday. Have a good weekend. Good luck studying.